Okay, Jane. So we were doing fission and fusion and the binding energy per neutron. So then let's do this question state. What is meant by binding energy? You can just copy the definition from the notes you are having, right? So yes, here, right? So yes, the variation with the nucleon number of the binding energy is shown. The question is, here is the nuclear reaction state. The name of this reaction, definitely it's a larger nucleus being split into smaller fragments. So it's the nuclear fission reaction, right, students? Okay. Mark the position of the uranium, molybdenum, and lanthanum. Uranium would be at the end. Molybdenum is 95, lanthanum is 139, right? So students, here is going to be exactly at the end, that is uranium, which is 235. Right, so now you can estimate that this top is 56, which is iron, right? This is for your information. Then 95 is molybdenum. Molybdenum is 95, so it will be somewhere here, right? And lanthanum is 139, so it will be somewhere not here, but it will be here, right? So lanthanum will be somewhere here, right? So this is how you're going to estimate the position. Okay, next point. Okay, now fission. Yes, so now let's go into the detail of these things. Fission reaction. It is a nuclear reaction in which a large nucleus, yes, a large nucleus breaks into smaller one by releasing large amounts of energy, right? So here is some example where we have uranium nucleus and it is split into dot of nuclei, these, and these are the neutrons which are released, right? So, okay. So students, a slow moving neutron, here is the slow moving neutron, this one, right, is incident on the uranium nucleus which ignites the fusion reaction and two smaller nuclei are formed, barium and krypton. So these are barium and krypton actually. Right, students, let's say this is barium and this is krypton. And then three neutrons are released with the emission of energy. Now, so what's going to happen in the fission chain reaction? These three neutrons are going to go to the other three uranium nuclei. So if I want to make the other three uranium nuclei, like let's say the other uranium nucleus is placed here, one is here, one is here. So what's going to happen? They are going to hit these uranium nuclei, and these uranium nuclei are going to undergo the fission reaction themselves. So they're going to again form what? Barium and krypton, and then three neutrons, right, students? And then barium and krypton from this uranium nucleus, and then three neutrons, right? And then barium and krypton from this uranium nucleus, and then three neutrons. So, students, how many neutrons are released in the second step? We can count them. Like this is like, let's say, 1, 2, 3, 4, 5, 6. And 7, 8, and 9. 9 neutrons are released, right? In the second step. So these 9 neutrons are going to go do the fission reaction in the other 9 nuclei. So the result is going to be this, like 3 neutrons in the first step, 9 neutrons in the second step, 27 in the third step, and this is going to go on, so on, right? This process goes on until all the uranium gets used up, called fission chain reaction, right? Okay. Now, what is a nuclear reactor? Fission chain reaction can be controlled. Fission chain reaction can be controlled, which is used in nuclear reactor to boil the water, right? Which in turn uses steam to drive the turbine and hence the dynamo to produce the electrical energy. Dynamo is basically the generator, right? And the controlling factors are graphite, heavy water, boron, or cadmium rods. Because they do what? They absorb the neutrons, right? Okay. So here is some schematic diagram of a simple nuclear reactor that we have. The control rods like made of boron, fuel rods made of uranium, right? Heat is going to boil the water and that is going to produce steam. Steam is going to go to the turbine. Turbine is going to drive the generator, which is going to produce electricity, right? Okay. Atomic bomb. It is an uncontrollable fission chain reaction, right? So, like if we are not able to control the nuclear reactor, it will become an atomic bomb. Okay, fusion. Right, so fusion is a nuclear reaction in which smaller nuclei are merged together to form a larger nucleus, right? Above reaction is an example of nuclear fusion here, that we have a deuterium and then tritium and it forms helium along with a neutron. And then there is energy emission as well, right? Okay, so how is fusion done? I have already told you it is only possible when nuclei are moved closer with high speeds to overcome what? The electrostatic repulsion, right? This requires large amount of energy to start. So fusion reaction, which is not possible on Earth. So fusion can only occur on sun and stars, where very high temperatures are available to get higher energies to move the nuclei towards each other with high speeds, right? Okay. So now let's get to the examples of the graph. Okay, so the technical topic of the chapter is coming. Graph. You know, students, graph shows the quantitative relationship between two physical quantities, right? An equation of the graph is basically used to calculate the instantaneous value of the y-axis at any time on the x-axis, right? For example, if we have like, yes, this equation, y equals to t, then the graph of this thing is turns this straight line, right? And if we talk about this y equals to t square, then you know, students, the graph is going to look like this, right? Y equals to t squared. And if we talk about y equals to t, then it's going to look like this curve, right? Okay, so, okay, so y equals to e raised to the power t is an exponential function, right? So, okay, so this graph starts from 1 and like this is going to be 1, right, students? So the starting position of the graph is going to be 1. And if we want to plot this 2 times e to the power t, then the graph is going to like be the shape of the same type, but it's going to start from 2. And if we have y equal to 50 times e to the power t, then the graph is going to start from 50 of the same shape. So it means the coefficient of this thing is going to be the starting position for the graph. Okay, now next graphs. If we have y equals to e to the power negative t and then we plot y versus t, then students, it's going to be looking like this, right? And it's this graph is going to start from 1 if you have a look at it. And if we talk about y equals to 10 times e to the power negative t, the graph is going to be same, but it's going to start from 10, right? So above these graphs, they are called decay graphs. What graphs? Decay graphs, right? And what were these graphs? This, and this. These are called exponentially grow graphs, right? Okay. Note that the coefficient of the equation is the starting point of the graph. Yes. Using the equation, an instantaneous value of y can be found at any time during the decay. Okay, so now let me remind you some basic properties of logarithms, right? Like if we have to, take the log of the product of two numbers a and b, then the individual logarithms would be like log a plus log b. And if they are being divided, then it's going to be log a minus log b, right? And if we talk about the third one, it is equal to actually b is going to go to the back. So log of a to the power b is going to become b log a. right? And what about anti-log A? Anti-log A means 10 to the power A, right? So you must know all four of these properties, right? Okay, so like log of 1000 is going to be log 10 to the power 3, or 3 times log 10, which is going to be log 10 is 1, so it is going to be 3. Log 10 is 1. Natural log E is also 1, right? So these are some very important things to do, the numerical things. Okay. Mathematical models of the radioactive decay. In any radioactive decay, students, let's say if I say that N naught is the initial number of nuclei, right? Then the number of nuclei are going to change to, let's say, N final value after some time delta T, right? Then this change in the number of nuclei, that is this delta N, is going to be called as N naught minus NF, right? The change in the number of nuclei, or the number of decayed nuclei, is basically the number of disintegrations of the nuclei one by one, randomly and spontaneously. So the number of undecayed nuclei after time t, they are going to be what? Delta n, sorry, n minus delta n, right? Or n naught minus delta n, right? So these are the remaining number of nuclei. Now, what is the probability of decay? Probability of decay is very simple. Probability is basically the change in the number of nuclei divided by the total number of nuclei, right? And okay, initial number of nuclei, right? So this is called probability of decay. It is definitely a unitless quantity because it is probability. Next is the activity. So students, activity is the number of disintegrations per unit time. It means we can call it rate of decay, like how many decays are occurring per unit time, right? So we define it as activity, and the activity is going to be mathematically written as A equals to delta N divided by time. And its unit is going to be just like frequency. If you remember, the frequency is number of oscillations per unit time. So the unit was oscillations per second. So we used to call it hertz. Remember? So if we talk about here, then the unit is going to be disintegrations, number of disintegrations per second, disintegrations per second. And what are we going to call us? It is called becquerel, right? So the symbol is capital B small q. So yes, okay. So next, reactive material constant. A measurement is constantly specific for a particular radioactive element, and that is called the rate of probability of decay. What? Rate of probability of decay, right? And what do we call rate of probability of decay? We call it decay constant. So let me try to make its formula. It's going to be rate of probability of decay. So it means probability ka rate, so divided by time. So this is called decay constant lambda. And probability of decay is delta n by n, so divided by time. So if we simplify it, it's going to be lambda equals to delta n by time into n. So students, if we have a look at this thing, then this is the activity. So it's going to be lambda equals to activity divided by n. So if we talk about this whole formula, then it is A equals to lambda n, a new formula for us in nuclear physics, right? Okay, next. Yes, sir. So what is half-life? Let's talk about it. You already know about that. It's the time during which the initial concentration or the mass or the initial number of nuclei or initial activity or initial count rate of the radioactive element is reduced to half of its value, right? So you have seen the graph of the half-life is going to be like this, and this is since an exponential decay curve. So here is we're going to use that concept of the graph that we learned today, exponential decay, right? So the y-axis could be all these things. What these things? Number of nuclei, mass of the sample, activity or count rate, right? What is a count rate? It is the rate per count, a rate of count per unit time, like counts per second or counts per minute, right? Okay, half-life variation, it is going to be definitely an exponential decay curve, right? Okay, so if we have, let's say, the number of nuclei, yes, the number of nuclei versus time graph, then it's going to be just like this, like number of nuclei is here and here is time. So the graph is going to look like this exponential decay curve. And I told you that this graph is going to be e to the power something. So n, and the starting point of the graph will be somewhere here. And let me call them the initial number of nuclei n naught. So this is going to be the coefficient of that graph, n equals to n naught times e to the power any constant into t with negative sign, because it's a decay curve. So what is that constant, students? That constant is lambda, the decay constant, which we learned as a equals to lambda, and we proved this formula previously, just already, right? Okay. So yes, so the instantaneous value of the number of radioactive nuclei at any time instant t can be found by the equation what? Yes, by the equation this, right? Where n is number of nuclei at any time t, and naught is the initial number of nuclei, right? At any time t, and lambda is the decay constant. E is a constant whose value is 2.71, right? Okay, so now let's go. The half-life of the graph of the activity is going to be looking like this. Like if this is activity versus time, then the graph is going to look like this, right? So if let's say this is the initial activity A naught, then the half-life can be calculated by going to the A naught by 2 value where the activity would be half. So this much on the x-axis is going to be the half-life, right, students? And how do we represent it? We represent it by T half. Okay. So students, A naught is the initial activity, right? A is activity after time T. Sometimes the calculated half-life of radioactive nucleus is less than the original half-life measured. And what are the reasons behind this difference? That there is what nature of the radioactive decay, this random in nature, background radiation, you also know from O levels, or sometimes we also know that that daughter product could also be radioactive. So these could be the reasons behind this statement, right? Okay, now let's go to the definition of the mole. Yes, students, you know it from chemistry. Mole is defined as mole mass in grams over molar mass. It can also be defined as number of particles divided by Avogadro constant. So we have this formula finally being formed. And now this proof is asked for 3 to 4 marks in exam. What they asked that prove that decay constant multiplied by half-life is equal to natural log 2. So let's start proving it, right? Our formula is n equals to n naught times e to the power negative lambda t. And if we have the activity graph, then the formula is going to be like this. A equals to A naught e to the power negative lambda t, right? Same graph with just the variable changes from n to a. Okay, so yes, so now you know that when the number of nuclei, like n, if let's say they become the half of the initial number of nuclei, then the time is called what? half-life, right? So let me put this value here. So it's going to be looking like at place uh, n, in place of n, I'm going to write what? N naught by 2, right? And equals to n naught times e to the power minus lambda. And in place of t, I'm going to write t half because it's a specific time, right? Half-life. So then n naught is going to be cancelled. So it's going to be half equals to e raised to the power negative lambda times t half, right? So if we reverse the exponents, then it's going to be looking like this, like it's going to become 2, and this is going to become what? E to the power lambda times t half, right? So now we're going to say that uh, taking natural log of both sides, taking natural log of both sides, so it's going to be what? Natural log of 2 equals to natural log e to the power lambda times t half, right? So, students, that this is the exponent. So this is going to go become the coefficient of the log according to the law. So natural log of 2 equals to lambda times t half times natural log e. So now you know that natural log e is 1. So we proved it. Natural log 2 equals to lambda times t half. So this proof will last for 3 to 4 marks, right, students? So let's stop for a minute because I think the chapter is finished. Yes, just 1 minute. Okay. So yes, chapter is finished. Let me do a question for you. Question number 13. First, they say the isotope of an element is radioactive. Explain what is meant by radioactive decay. So radioactive decay is what? There are 3 marks. 1 mark is for saying that it's a spontaneous decay. And 1 mark is for saying it is a random decay. So spontaneous and random breakdown of nucleus of a nucleus, and the 1 mark is for writing into alpha particles, beta particles, and gamma radiations. Right, sure. Okay. So the next part is the number of, yes, the question is, at time t, a sample of radioactive element contains n neutrons, and after this time, the number that decays is delta n. State the expressions for the number of undecayed nuclei, right? So undecayed nuclei is going to be like this, delta n, sorry, the initial are n, and the decayed are delta n. So if I subtract them, then this is going to become undecayed number of nuclei. The mean activity is delta n over delta t, right? And the probability of decay is delta n over n. And the decay constant is delta n over time because it's the rate of probability of decay, right? I have done it for you above. Okay, next question. Yes, next part is if the activity versus time graph is given and it is going to vary like this, and this is for the sample of the radioactive isotope, then the question is, decays to form a stable isotope S. There are no nuclei in the sample at time t equals to 0. Now we have to draw the number of nuclei for the daughter nucleus. So this was the parent nucleus. So students, if in the first half-life they were reduced to like uh, 1 and 1, 2 divisions, so the daughter nucleus is going to increase by 2 divisions. So after first half-life, this is going to be the first point. It is going to start from origin definitely. And then in the second half-life, like from here to here, the number of nuclei that are decaying from point X to point Y. So there is a decrease of 1 division. So there is going to be an increase of 1 division here. So this is going to be the next point. and next time it like changes by half of the division, so it is going to be increasing by half of the division. So we're going to, you know, join all these points to get a graph, a best fit line. And for that, we're going to have how many marks? 2 marks, right? Okay. So next question, what is meant by decay constant? Okay, I've just told you, you can copy the definition, and then they are asking to prove for 3 marks. For 3 marks, this delta lambda times t half equals to 0.693, right? So 0.693 is what? It is basically natural log of 2 that we just proved. And this question is also for 3 marks. Okay, the next question is, the next part is this, yes. Initially, the count rate is 538 per minute. So this is activity. After time, 8 hours. So this time, the measured count rate is this. So this was A naught, so this is A. So the question is, estimate the half-life. Okay, how can we estimate the half-life? The question is A equals to A naught times e to the power negative lambda t, right? So let's first calculate the lambda. So it will become like this, A by A naught equals to e to the power minus lambda t, or we can take the natural log of both sides, so it's going to look like natural log of A divided by A naught equals to natural log of e to the power negative lambda t. So it's going to be like negative lambda t times natural log e. So natural log e is 1, so negative lambda t equals to natural log of A divided by A naught. So we can now put the values, like what values? Like we're going to make the lambda the subject to the formula, natural log of A divided by A naught. A is 228 and A naught is 538 divided by minus t. So that is in hours. So we have to convert it into minutes first because this thing is given in minutes, right? So it will be 8 times 60. So let's do it. 8 times 60 and let's calculate it. Like you're going to take your calculator, 228 divided by 538, and you're going to take the natural log of that thing. You're going to get negative 0.85, and you're going to divide it by 8 and then 60 as well. So you're going to get students lambda as what? Your value of the lambda will be what? 1.78 times 10 to the power negative 3 per minute. Right, students? Okay. So now next thing is we have to convert it into hours. Like how? Like we're going to if we have to go from minute to hours, we'll be like dividing by 60, but this is per minute, so we're going to multiply it by 60. So this is going to be lambda equals to 0.107 per hour, right? So now we know the formula for the half-life times lambda equals to natural log 2. So half-life is going to be what? Natural log of 2 divided by lambda is 0.107. Right, so yes, so let's start doing it. Times natural log 2. So this is 6.5 hours. Okay, half-life. Now next is the accepted value of the half-life is 5.8 hours. Like they are talking about the experimentally. This is the theoretical value, but the experimental value was 5.8. So they are asking about the two reasons uh, which cannot be explained by the faulty equipment of this thing, the difference. So I have told you these reasons here. Yes, these three reasons that the nature of the radioactive is random, or there could be background radiation, or the daughter product may also be radioactive. So you can put any two out of these three there, right? Okay, students, so you can attempt the next questions yourself. They're not difficult, right? So our chapter is finished, and thanks.